Okay, fine. So in our previous classes, we learnt the usage of elements of symmetry and symmetry operations, which are basically meant to classify the molecules into symmetric, dissymmetric, and asymmetric types. And this classification is relevant from the point of stereochemistry, because we will see later that dissymmetric and asymmetric molecules are chiral. What is the meaning of chirality? Those things we will see later. Now, in fact, in my previous class, I had made a passing reference to a point. What was that? That this three-dimensional molecules structure writing on a two-dimensional plane like a paper or a board becomes incomplete, is it not? So, like we have we have these formulas. I mean, what are the two formula we are used to? We are very much used in chemistry. One is molecular formula, the other is structural formula. But today we are going to see a new formula called projection formula. What is the need for projection formula, first of all? That's the question. Take an example of a molecule: chloro, bromo, fluoro, iodo, methane. This is nothing but a methane substitution. All four hydrogen atoms of the methane have been substituted, and you get a molecule like this. But what is the structure of this molecule? Geometry of this molecule? Naturally tetrahedral, because the carbon is sp3 hybridized tetrahedral molecule. Now, when the molecule is tetrahedral, automatically it means the molecule is three-dimensional, is it not? Because tetrahedron is a three-dimensional picture. Now, I mean three-dimensional object. Now, if I ask you to write the structure of this molecule, showing its three-dimensionality, is it possible to write it on a piece of paper, on your notes, or on my board, blackboard, or even a computer screen? Is it possible? No, not at all. Because how can you show a three-dimensional molecule on a three-dimensional three-dimensional molecule on a two-dimensional paper? Then the best I can do is I can write it like this: carbon, 4 bonds, and all 4 bonds connected to different atoms. But does this give correct picture of the atom, the actual real picture of the atom? Definitely not. Why? Because this shows, if somebody is viewing this to the viewer, writing like this shows that maybe all 4 atoms are on the plane of the board, is it not? So maybe the compound can be planar. It gives a picture like this. Of course, I know and you know, but methane is tetrahedral, it is a three-dimensional picture. But somebody who is seeing it for the first time gets a wrong idea. Of course, for simple molecules, we know the geometry is fine. But when you are depicting the structure of large molecules with too many tetrahedral carbon atoms, then which substituents is where? What is the relativistic positions of substituents in space? These things we have to address. Then, of course, we become uh, under-equipped if we have only formulas which can give us two-dimensional structure. That's why I tell we become under-equipped. Therefore, to address this challenge, what is the best way? There is one way: you work with models, because models are three-dimensional in nature. I mean, you can construct model of anything. You can construct even model of Taj Mahal and give it to your friend. So model of anything can be constructed. There are different approaches to construct models of molecules. One is called a ball and stick model. This is a ball and stick model. Why do we call this ball and stick? The atoms are balls and the connecting bonds are sticks. You work with models. Simple. But is it possible that always we work with models? Always? Every time when we discuss stereochemistry, or every time when we have to write the structure of a three-dimensional molecule, I have to construct models? Impossible, because we communicate through writing, and this writing is always on a plane. We communicate like that. We want to tell our thoughts, express our thoughts through writing. So how to address this problem? To address this problem, we have devised a new formula called projection formula. Okay, so how best this molecule can be depicted like this? Okay, fine, don't worry. What are the meaning of all these things? Don't worry, that we will see later. You look at this picture. In fact, even this is not the best depiction, although it should be a wedge here. No problem. You see the models, the actual models of different molecules. This picture shows 1, 2, 3. There are 6 molecules, molecular models. And you know how a tetrahedral model looks like, right? Almost like a pyramid. It has 3 atoms which are sitting on the floor and 1 atom at the top, and the carbon atom is at the center. So in fact, you can also create a pyramid where carbon atom is inside the center of the pyramid and all these 4 atoms are pointing towards the corner of the pyramid. Okay, fine. So this is the ball and stick model of different molecules. You can best way to understand the structure is have a ball and stick model. But you know, as I told you, it is not always possible to have ball and stick model for millions of molecules, which we come across. Of course, one cannot come across millions of molecules, which an organic chemistry or as such come across millions of molecules, ball and stick models impossible. But anyways, if it was a direct class, physical class, I would have actually worked with models and made you understand how to write the projections. But you know, these virtual classes, there is a limitation, and the limitation is this: with when it comes to demonstrations, our online classes fail basically. Anyways, this is the best thing what we are doing. Hope things will get better soon and we can have direct meetings later. Fine. So what is the solution we have made? That we have devised projection formulas. In fact, what is a projection formula? A configuration of a molecule that is 3D is represented on a 2D paper. So how to do this? This is what projection formula is. In stereochemistry, in organic stereochemistry, we have 4 different projection formula, which are called Fischer projection, Newman projection, Hasse-Horst projection, wedge-dash formula. In fact, wedge-dash formula or wedge-dash projection is also called flying wedge formula, flying wedge projection. The usage of terms projection and formula sometimes goes synonym. Like in some texts, you will see Fischer projection. In some texts, you will see it as Fischer formula. But both mean same, projection and formula. Let us now look at each projections one by one and understand how to represent the 3-dimensional structure of organic molecules using these different type of projections. Okay, let us start with this flying wedge or wedge dash projection. Both mean same. Sometimes it is referred as flying wedge and wedge dash, but I would rather use the wedge dash projection. Okay, fine. So what is the main difference in the wedge dash formula than the ordinary structural formula? In ordinary structural formula, what you write like this, you have like this. Even if you write a molecule like propane, how do you write? C, 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 3C and all H on the connections on the carbon atoms. Is it not 3 plus 3 plus 2, 6, 7, 8 hydrogens you have. But you know, while you write that, all lines will be simple lines. When you write the structural formula of propane or ethane, for example, CH3, CH3, C, HH, HH, H3, 6H, all hydrogens and carbon bonds are simple lines. You are showing like that. So in the wedge dash formula, there is a deviation from this. We don't represent all bonds using simple lines. Rather, how many bonds a tetrahedral carbon atom has around it? 4 bonds. So out of these 4 bonds, 2 bonds we represent using simple lines, plain lines, normal lines. 1 bond using a solid wedge like this. So what is a solid wedge? It is a thickened line like this, solid wedge. As well as last bond, the 4th bond, we represent by a broken line called dashed wedge. Dashed wedge. This is a solid wedge and this is a dashed wedge. Sometimes instead of dash wedge, simple broken line is used. Okay, so what is the deviation now? The deviation is simple. Instead of writing 4 simple lines around the tetrahedral carbon atoms, we write 2 simple lines, 1 wedge dash solid wedge. The one is the dashed wedge or the broken line. How does it turn out when we write the projection, wedge dash projection of methane? How does it look? So now you see here, this is the ball and stick model of methane. Now uh, we have a orientation of viewing all these projections. In fact, methane can be represented using Fisher's projection as well as wedge dash projection. Whichever projection I use, the structure, three-dimensional structure of methane is same. Is it not? Ethane, for example, you can represent it through wedge dash, Fisher, Newman's or Horse. But I can use whatever the projection of my choice, but the actual structure of ethane should be correctly represented. Is it not? So how do these projections vary from one another? What is the variation? What is the distinction between these projections? The distinction is only in the angle of viewing. How do I, from which angle I look at the molecule, or from which angle or which orientation of the molecule I am looking at. That is the difference between one projection to another projection. Okay, so in the wedge dash projection, which is the angle we are looking at? Which is the angle we are looking at the wedge, in the wedge dash projection? In the wedge dash projection, we are looking the molecule from a side view, in the sense, see, this is the ball and stick model of methane, right? You look at this molecule in the way I am looking at, from, like, you are the viewer, you look at this. In that angle of viewing, in that orientation, if there is a plane here, how many atoms come on this plane? How many atoms come on this plane? 3. Is it not? 1 hydrogen, 1 carbon, the other hydrogen. And what about the remaining 2 hydrogens? 1 hydrogen will be out of plane and projecting towards you. The other hydrogen is also out of plane, going away from you. So 1 hydrogen is towards you, 1 hydrogen is away from you. These towards and away hydrogens are out of plane. We also call above the plane and below the plane. But these 2 hydrogens are in plane. You can place plane anywhere. You can also place a plane like this. Any plane you place will have maximum 3 atoms on it. This molecule is sitting on the floor, example. That floor is a plane. How many atoms it is containing? 3 hydrogens. Is it not? So what is the first distinguishing point? That in a tetrahedral molecule like this, like simple tetrahedral molecules like this, or even complicated ones, tetrahedral molecules, a plane you choose can accommodate maximum of 3 atoms. Any plane you choose can accommodate maximum of 3 atoms. So even while writing our projection, we will accommodate maximum number of atoms on one plane, because atoms on a plane is easier to view and understand, like we have done here. You see this? The bond which is on the plane of paper and the bond which is on the plane of paper, 2 bonds and a carbon. These 3 atoms are in plane. These are in plane atoms. So if I write a simple line, what does it mean? Those 2 atoms are in one plane. These 2 atoms are in another, is on the same plane. That means hydrogen, carbon, hydrogen. These 3 atoms are on a plane. Simple. Is it not? How to represent the remaining 2 hydrogens which are out of planes and towards and away from you? The solid wedge, please remember, the solid wedge represent an atom towards you, out of the plane, and towards you, out of the plane and towards you. The dashed wedge or a dashed line is out of the plane, away from you. Okay. So if I write a structure like this, then this will be much more nearer to the actual structure. Instead of writing all hydrogens using same simple lines, if I write 2 hydrogens using simple lines and the other solid wedge, the last one flying dashed wedge, isn't it more meaningful than the simple structure? Yes, of course it is more meaningful. Why it is more meaningful? It is now closer to reality. It is actually nearer to reality now. Therefore, this becomes a projection formula. If I write simply 4 lines, it just becomes a structural formula. If I distinguish the lines to accommodate the three-dimensional structure, then this becomes a projection formula. So do you understand how to write structure, three-dimensional structure of tetrahedral molecules using projection, wedge dash projection? 2 atoms in one plane, other 2 atoms out of plane, one projecting towards you, the other projecting away from you. That is what they have done here. You see, they have converted this ball and stick model into a wedge dash projection. Please understand the word usage here. The ball and stick model has been converted to wedge dash projection. Okay, so the top hydrogen on the plane, this hydrogen is also on the plane. The hydrogen towards you is represented by a wedge dash. The hydrogen away from you is also is represented by a dashed wedge or a dashed line. See, it's a dashed line here, not dashed wedge. Dashed line is many a times used than a dashed wedge. Dashed line usage is more common than dashed wedge usage. Okay, fine. So whenever you come across such representations, a solid wedge and a dashed line, please remember this is a three-dimensional molecule. Okay, and the structures correspond and the bonds correspond to the structures accordingly. Okay, see now, there are different ways of writing the projections. These are all the most common ways of writing wedge dash projection. Good ones, good ones. But you should better avoid writing like this. For example, plus mark type. Don't write a wedge dash like this. And don't write a wedge dash with very close angles between the bonds like this. Very acute angle between the bonds. Don't write. Nor don't write it like this, where two planar bonds are aligned vertically. Don't write like this also. So what is the best way of doing this? You always keep the planar bonds in an obtuse angle. So hope you understand the meaning of an obtuse angle. Planar bonds, you always keep an obtuse angle between them. See, whichever the projection I am using, it is always greater than 90 degree. Greater than 90 degree, obtuse angle, obtuse angle, obtuse angle. And keep an acute angle between wedge and dash. I'm sorry, solid and dashed wedge. Keep an acute angle lesser than 90 degree. Then it looks better. Looks better. Okay, these are all standard usages. Fine, whether it looks better or doesn't look, it is subjective. It is up to individual choices. For few of you, this may look better, but these are all standard usages which we have to stick to while learning things. We have to stick to standard usages. Now come to fissure projection. This fissure projection is having line bonds which are represented only by simple lines. Okay, then the problem, all 4 simple lines if I write, doesn't it mean that I am wrongly representing the three-dimensional structure? It should mean like that. That is what the discussion we made before. But in fissure projection, there are some standard or important assumptions while writing the structure. There are some assumptions. What are those assumptions while writing the structure? Okay, first of all, fissure projection is a flat representation of a 3D molecule. There are no wedges used in this projection. All are simple lines used in this projection. Flat representation of a 3D molecule. A chiral carbon, okay, or any carbon, even if it is not chiral, achiral, a tetrahedral carbon example, is represented at the intersection of 2 lines, horizontal and vertical lines. Example of fissure projection which I have shown here of an alcohol, secondary alcohol, as a vertical line and a horizontal line. All fissure projections have vertical lines and horizontal lines only. In fact, there will be a single vertical line in any fissure projection and many horizontal lines depending on the number of carbon atoms. Anyways, or depending on the carbon skeleton. Flat representation of a 3D molecule. As I told you, there is an intersection between the horizontal line and the vertical line. At that intersection, carbon is placed. The carbon around which the bonds you are representing, that is placed. What is the main assumption here? That's what I told you, right? What is the assumption here? This is the important assumption. I mean, you listen to this carefully, bit important. Horizontal lines are forward out of plane. Vertical lines are behind the plane. So that means there is only the carbon, central carbon, which is on a plane of your choice, plane of your reference. The two substituents, there are 4 substituents for a carbon, right? The 2 substituents are towards you, that will be represented on horizontal line. The 2 substituents which are away from you are represented on the vertical line. Okay, so carbon chain is always represented on the vertical line. And there is one more assumption: highest oxidized carbon is placed at the top. Always highest oxidized carbon is at the top. Anyways, don't worry about these things. 180-degree rotation in the plane is allowed, 90-degree rotation is not allowed. We will understand more about these points when we take up interconversions between projections. So if I give a molecule in Fischer projection, you have to convert that to all other 3 projections. That exercise we will do in the next class. Then I will explain more detail 180-degree rotation, 90-degree rotations in plane, out of plane. Okay, fine. Now let us see how a Fischer projection of this molecule, the same molecule, yeah, the chloroiodo bromobutane. Instead of chlorine butane, I have just represented the substituents as 1, 2, 3, 4. Now I hope you have understood the ball and stick model, right? It is easier to understand ball and stick model. So these 2 atoms, 1 and 2, are in one plane. Fourth atom, 4. Now atom 4 is towards you, out of plane. Atom 3 is away from you, out of plane. Now I told you these projections vary from one to another on what? On simply the angle of viewing, from the orientation point of view. How do we view the molecule? From that point, the projections differ. For Fischer projection, okay. Now, where are you viewing the molecule for wedge dash projection? I told you from this angle, where 2 atoms are on plane and these 2 are out of plane. For a Fischer projection, you have to view the molecule from here, basically. From here, you have to view the molecule from here. If you view the molecule from this point, how do the substituents 4 and 3 look like? They are coming towards you. Is it not? How do the substituents 2 and 1 look like? They are going away from you. Only the carbon is the reference point. With respect to this reference point and your view angle where you are viewing at, the 4 and 3 is coming towards you. 2 and 1 are going away from you. Is it not? Now, you can orient the molecule in this way, where 2 substituents are coming towards you, 2 substituents are going away from you. Through how many angles? Through 4, through how many points of viewpoints? Through how many viewpoints? 4. You can look from here. Similarly, you can look from this angle also. Is it not? When you look from this angle, which are the substituents towards you? 4 and 1. Which are the substituents away from you? 2 and 3. So you write those substituents like this first. You are viewing from this angle. 4 and 1 are towards you. So all those towards substituents I write using a wedge, solid wedge. All those away substituents I write using dashed line. Okay, like this. Now simply convert this solid wedge into a horizontal line, dashed wedge into a vertical line. Where is the carbon? Carbon is at the intersection of these 4 bonds. What is the difference between a structure using wedge dash I have written here? I could have used this. Why am I using this now? It is simply this. Always remember, in fissure projection, the central carbon atom is not shown. It is only the intersection point. Never write a carbon in fissure projection here. This is the most common mistake the students do. They write a carbon and try to write a fissure projection. It is not a fissure projection. In fissures projection, that's why it's an assumption. You can have in your own way projections, but what fissure has given the projection we should follow. Carbon is never shown. It is always an intersection point of the vertical and horizontal lines. So don't write. Now take the lactic acid example. View the molecule from this angle and convert it into fissure projection. So I am viewing like this. Which are the substituent towards me? OH and H, which I have written like this. Which are the substituents away from me? COOH and CH3 away from me. So COOH, CH3. Solid wedge, convert into an horizontal line. Dashed wedge, convert into a vertical line. And don't show the carbon here. So this is the fissures projection of lactic acid. You can ask me a question. Why I did not view the molecule in this angle where COOH and CH3 are coming towards me? I could have viewed in this angle. OH and H are going away from me. COH and CH3 are coming towards me. Why I did not choose that angle? Because there is one more assumption, important assumption in fissures projection, that in case there is an oxidized carbon containing alcohol, aldehyde or carboxylic acid, that has to be on the vertical line at the top. Therefore, I choose an angle in which the COOH will be away from me. So away substituent will be on the vertical line always. That is the assumption of fissure projection. Substituents which are away are on the vertical lines. Substituents which are towards us are on the horizontal lines. So I have chosen an angle to satisfy the fissures assumption of keeping the highest oxidized carbon at the top of my structure projection formula. So this is the correct fissure projection formula of lactic acid. But what is S lactic acid? What is R lactic acid? L and D lactic acid? Don't worry as of now. This we are going to take up later. The configurations. Of course, again, I've just put it one more molecule, a diol. View from this angle, H and OH will be towards us, CH2OH of the top, CH3. Again, you can ask me a question. Why I did not choose this angle? Because of another assumption of fissure projection. What is that? On the vertical line, I have to place my carbon skeleton. Please remember. Where is my carbon skeleton? Which is my carbon skeleton? 1, 2, 3. And the numbering, this IUPAC numbering, 1, 2, 3. The 1, 2, 3 carbons have come on the vertical line in the fissures projection. Please note this. Very important assumption or very important step while writing fissures projection. Where are my 1, 2, and 3? Here are my 1, 2, and 3. The other substituents OH and H, because I am viewing from this angle, OH will be towards my right and H will be towards my left, but coming towards me, and therefore coming towards me, and therefore they are written on horizontal line. Okay, fine. The same thing I have done. COOH, CH2OH. Why I have shown you this example? Because there are two oxidized carbons, COOH and CH2OH. Which one is highest oxidized? COOH. Therefore, I am placing this on the top of the projection formula. Okay, please, of course, I must tell you that hearing 2 hours of explanation is not equivalent to writing down yourself and working out the problems. Only then you will practice these things, writing projections and interconverting them. Anyway, in my next class, I'm going to give you exercises as well as some problems to work as homework and submit later. Yeah, that's what. COOH is more oxidized. That's why I've placed it on the top compared to CH2OH. If there was no COOH, this was CH3 example, then I have to place CH2OH on the top because CH2OH becomes highest oxidized if there is CH3 here. Okay, fine. So, okay, fine. So you are sending your names. Please send your names for the attendance in the chat box. Okay. Now, these are all different examples of Fisher's projection which I have given you to make you understand how to write the structures. Now, this is the last example we are going to study in this class. That is, if there are two carbon atoms which are chiral, I mean, like I told, don't worry about chirality now. I'm just you understand from structure point of view. If there are two molecules which are two carbon atoms which are chiral in the same molecule, then how to write the Fisher's projection? Look at this. Look at this. In a representation of a molecule, usually the carbon skeleton is written in zigzag way. How many carbon atoms are there in the skeleton? C1, C2, C3, C4. Is it not? So this is written in a zigzag way, like this, like this. If there is one more carbon, then you will write like this, zigzag. Okay, this is called puckering of the chain. Why zigzag configuration is required? Even that we were going to discuss later. So if you write a zigzag carbon skeleton like this, carbon skeleton is zigzag. Then where are your substituents? Two substituents like this, two substituents like this. They are anti in nature. They are anti-parallel in nature. But for an anti-parallel conformation, that is called staggered conformation. We will take up Newman's projection and understand staggered conformation later. For a staggered conformation, you cannot write Fisher's projection. So you have to rotate this by 120 degree and take these two bonds which are anti to AB, parallel to AB, eclipsed to AB. So AB, and then if you rotate it 120 degree, you get C and D. Now you write Fisher's projection. The carbon skeleton on the vertical line, is it not? So where is your angle of weaving? You are weaving from here, from the bottom. See here, you are sleeping and weaving from the bottom. That is why I just picture is shown here. This is the picture of a viewer. He is just seeing from here. So if you are seeing the molecule from here, your C1 comes here, C2, C3, C4. A and B will be towards you now when you are weaving from here. So A, B, C and D will be towards you again, C, D. But what is the relativistic orientation of A, B, C, D? Please remember, when you are seeing here, A is towards you, towards your left. That is what I have written here. B is towards you, towards your right, towards right. In this C, on this C3, which is the one which is towards left? D. D is towards left. C is towards right. Okay. So now once you write this, it is easier to convert to Fisher's formula. Just write vertical line and write horizontal line. Please note again that I have not shown carbons as C at carbon C, just an intersection in the projection. So this is regarding Fisher's projection. So the other two projections, Newman and staggered, we are going to study in next class, and we will also start the exercise of interconversions of projection. Okay, fine. So